Hey guys, welcome back to this AP Calculus 2025 BC exam review. Today we'll be solving separable differential equations, which is a type of differential equations you'll see on FRQs, and you'll be asked to solve them. And we're only going with separable because those are the ones you need for the AP Calculus BC exam. In a multiple choice question, you might have a non-separable one, but they usually give you conditions or other information that'll help you to solve, even if it's non-separable. But separable is the one you will only see on the exam. So let's get into it. So as a reminder, a differential equation is an equation with a function and derivatives in it. A separable differential equation is a differential equation, so that you can separate all the variables and its differentials on one side and all the variables and its differentials on the other side. So an example of a separable differential equation would be something like y dy equals x dx. So here we have differentials, and it's separable because we were able to get all the y terms with the y derivatives on one side and all the x terms with the x derivatives on the other side. So to approach a separable differential equation, what you have to do is first separate the differential equation, right? Because usually they're not going to give it to you in this form. You have to separate it yourself. Then you have to integrate each part. Then after you integrate, you add a plus c on the side with the independent variable. So in this case, x will be the independent variable on the independent variable. And then you make sure, if it's asking you for a function, you make sure you have a function at the end. And you do that by getting it in the form y equals some expression. And as a bonus step, sometimes they ask you to find the only solution. This will just give you the general solution for the differential equation, but sometimes they ask you for a specific solution, which you just solve by plugging in the initial condition. Okay, so now we know the process. Let's go through a couple examples just to see how we do it. So we'll go with the easy one first. Let's do dy of dx equals 2x plus 4. So the first step here is to separate. So we separate the variables. There's no y term, so we just do dy. Multiply both sides by dx, we get 2x plus 4 dx. So you might be wondering, where do we put the 4? Well, when we're doing these differential equations, it's usually easy just to keep the 4, or any constants, right, with the x term, with the independent variable, because it makes it easier when we're trying to make it into a function. Next step, we integrate. So if we integrate that, we get y on this side equals x squared plus 4x. Third step, we add c to the independent variable. 4 is already done because we have it into y equals expression. And that's the solution for this differential equation. Next, let's say we have the differential equation dy over dx equals negative sign x plus 5 over y. Sorry, so the first step is to separate the variables, right? So we get y dy equals negative sign x plus 5 dx. We integrate, we get y squared over 2 equals, so here we say u equal to x plus 5, du is equal to dx, right? So this becomes just negative sine u du, which then becomes the integral of that. which then just becomes cosine of u, right? So in this case, it equals to cosine x plus 5 plus constant. So now we have to get y by itself, right? So we multiply both sides of the equation by 2. So we get 2 cosine x plus 5 plus 2c, right? So what we want to do is we want to, because we're multiplying 2 by c, and c is just any value. So we can call this c1, and if we call this c1, we can call 2 times c1 equal to c, and now we can just call it plus c. I'm not sure if this is necessary on the exam, but I think it's just helpful just in case they get picky about it. Now we have to use square roots, and we get y by itself, and the final answer is 2 cosine x plus 5 plus c. And that's how we solve this one. For our final differential equation, we'll do one with an initial condition. So let's say we have the question dy over dx equals 3 x squared e to the 2y, and we have the initial condition that y of 1 equals 0. So in this case, we have to separate the variables. So we do e to y dy equals 3 x squared dx. Now we integrate. We get e to the 2y over 2 equals x cubed plus constant. So from here, we can either plug in our initial condition to find c immediately, or we can just keep going with this until we have a function like this and then plug in. In this case, I'm just going to keep going with this and then plug in an initial condition at the end, but it's up to you which way you want to do. Just do whichever way is faster. So here, e to the 2y equals 2x cubed. We're going to do the same thing as last time. c1, 2c1 equals c plus c. We take the ln for both sides to get rid of the e. We get 2y equals ln of 2x cubed plus c. Then we divide by 2. We get y equals ln 2x cubed plus c over 2. Now we can plug in our initial condition. Our initial condition states that when x equals 1, y equals 0. So 0 equals ln of, 2x cubed, x is 1, so 2 plus c divided by 2. So really, we're trying to find out when this ln of 2 plus c equals 0. Well, it equals 0 when c equals -1. So our final answer would therefore be y equals ln 2x cubed minus 1 over 2. And that's our final answer for this differential equation. So that'll be it for today, guys. Thank you guys all for watching, and be sure to subscribe for tomorrow's video, and also leave a comment down below giving your feedback. Once again, thank you guys all for watching, and I'll see you guys all tomorrow. Bye.